How is resistance affected by temperature? Well, generally the resistance is increased when the temperature is raised. Again, this principle is used in fuses. A fuse wire has a certain resistance and will allow so much current to go through it, and it produces a certain amount of heat. Now, if the current is exceeded, then the temperature increases in the wire. This increases the resistance, which increases the heat even more. Eventually, the wire reaches its melting point and breaks the circuit. That's what fuses do. They let so much current through, but if you exceed the current, it overheats and it melts, and it reaches melting point, it breaks the circuit. Now, what happens if you've got more than one resistor in a circuit? In other words, in series, as you can see here. As you can see here, there's 3 resistors in a circuit. Now, there would be a voltage drop across the whole circuit, and each resistor would have its own voltage drop across it. So across each of these 3 resistors, they would have a voltage drop. Now, it's very important to understand that these resistors all have an impact on the amount of current flowing through the circuit. However, the same current is flowing throughout the circuit. So they all have an impact on dropping the voltage, but in the whole circuit, when it's flowing, it's the same current. In order to explain this, I want to make sure you discuss various circuits that you may have come across, and then we're going to carry out some examples to explain this whole subject to this. Firstly, I want to look at circuits in series. This shows you a circuit with a light bulb in it. Now, if you ignore the resistance of the wire, what would be the current in the circuit be? Well, if you put in known variables, you know that I equals V divided by R. The current in that circuit is 3 amps. So it's I, 6 divided by 2, it's 3 amps. What if you put another resistor in, such as a kettle, with a resistance of 3 ohms? So we've put that in now. Well, all you do, as they're in series, is you add their resistance. That's all you do, is you add their resistance. So now the resistance is 2 plus 3 is 5 ohms. Now you put them in the formula, you get a current of 1.2 amp. So do you see how connecting these resistors in has an effect on the current flowing? What if you put another one in? What if you put an iron in the circuit with a resistance of 4 ohms? What would be the total resistance? Well, all we do now is you add those resistances up, you get 9 ohms, add them all together, you get 9 ohms. Put them in the variables here, I equals 6 divided by 9. Now the current in the whole circuit would be 0.6667. So when they're in series, you add them. Now, don't forget, the current is dropping because much of the potential difference or voltage is used up in forcing the electricity through each of the appliances. It starts at the battery, it gets to the first resistor, and it loses electrical voltage trying to get through the first resistor. Then it goes to the second one and it loses potential difference getting through that one. Do you see there's a voltage drop at every point in that circuit? No. So if you ignore the resistance of the wire, ignore the resistance of the wire and ignore it, what would the voltages be at these points? A, B, C and D. Yeah, can you see those points A, B, C and D? What would they be? Well, at point A, because we're ignoring the resistance in the wire, there's no drop. So the voltage here would be 6 volts. It's the same as at the battery there. That's 6 volts. At point B, the current has had to travel through the first resistor and it will have lost electrical potential. So how do we determine the voltage drop? Well, this is the formula we said before, V equals IR. Now we know that with all 3 in a series circuit, the current was 0.667 amps. So first of all, you've got to work out the current in the circuit, and then you can work out the voltage drop. So we know the current is 0.667 amps. So put in this resistance, so that we know the resistance of the light bulb, the voltage drop would be 0.6667 times 2. So the voltage drop across that point would be 1.334 volts. So 1.334 volts of the total potential would be used up forcing the electricity through the light bulb. Therefore, the voltage at point B here, this voltage at point B, would be 6 minus 1.334 is 4.6666 volts. You understand? The voltage there, if you put a voltmeter there, you would get a voltage of 4.66 volts there. Let's determine the voltage at point C. Okay? Well, let's first of all, to do that, we've got to determine the voltage drop as the electricity has to go through the kettle. Now we know again, all 3, we've got 0.667 amps, so we know the ampage. You put in there, V equals 0.667 times the resistance, which is 3, times that out, the voltage drop here is approximately 2 volts. So 2 volts of the potential difference would be used in forcing electricity through the kettle. Therefore, the voltage at point C would be 4.667 minus 2. The voltage there, if it was taken and voltmeter reading there, it would be 2.667 volts. Do you understand? Let's determine the voltage at point D. Well, we know this is at the end of the circuit. It's at the end of the circuit, and if you ignore resistance in the wire, the voltage here would read 0, because all the last potential will be used in forcing electricity through the wire, and that's why we've worked it out. In other words, it would be 0 there if you ignored the resistance in the wire. It's not going to be 0 because there will be some energy there to force it round to the end. However, if you ignore the resistance, that's what it is. So do you understand that every point you get a voltage drop? If you put a voltmeter in, you took a voltage reading at different points in the circuit, you get different voltage, but the current is always the same.